We've talked about the fundamental dimension of length and described it in the context of length in the x direction. Let's recognize the multidimensionality of space by recognizing there are lengths in other directions. For example, we might pick an orthogonal direction and arbitrarily call it y, as we might do in a Cartesian coordinate system. Orthogonal is just a fancy word that describes how values for y can change independently of values for x. Now that we can characterize space in two orthogonal dimensions, we can define the familiar spatial property of area. Area might be thought of as having dimensions of its own, but its dimensions are more commonly derived from the more fundamental dimension of length. Your intuition may already be suggesting to you that those dimensions might be something like the square of length, and your intuition would be correct. But let's derive that dimension algebraically. First, we recall from geometry that the area of a rectangle is calculated from the product of the length of its base times the length of its height. We can convince ourselves that the dimensions of length squared is logical for area based on carrying dimensions through the algebra of the right side of this equation. That derivation is fairly straightforward, demonstrating why the derived dimensions of length squared make sense for a rectangular area. The fact that this derivation makes sense introduces the idea of dimensional consistency of equations. When the mathematics are derived from logic that is independent of any given set of data collected, the dimensions of the mathematical terms will agree. Here, the geometric logic is supported by the dimensions of the left side term in the equation agreeing with the right side term. In this case, the independent logic supporting the dimensional consistency comes from geometric theory. A consequence of dimensional consistency is that any consistent application of units will work for this equation. For example, we can use either inches or centimeters for the lengths of the base and the height, and get corresponding units of square inches or square centimeters for the area. This is the foundational theory underlying why we carry units through calculations with dimensional consistency to help us double check if we have plugged appropriate numbers into the equation. As it turns out, you don't have to use a rectangle to convince yourself that the dimensions of area will always be length squared. Let's see if we can follow the same path of logic with a circle rather than a rectangle. The intuition that area is length squared is not so obvious here, but let's use theory to demonstrate that it still holds. Theory from geometry and calculus provide us with a well-known equation for the area of a circle, which is pi times the square of the radius. Again, our job here is to demonstrate the dimensional consistency of this equation, which means we need to determine if pi times the square of the radius indeed works out to be a square of length. The first challenge is to determine the dimensions of pi. You may want to pause the video here and challenge yourself to see if you can work this out on your own. I'll give you a hint that you will need to know the definition of pi, and that definition has something to do with a ratio that describes the geometry of a circle. I'll give you a chance to pause the video here, but I'm going to move on. The definition of pi is the ratio of the circumference of a circle to its diameter. This turns out to be the same number no matter how large or small the circle is. I'm using the equals sign with 3 bars to emphasize that this is more than an equality but a definition. You can read the 3 bars in English with the phrase is defined by. We can now carry the dimensions of circumference and diameter through this equation to determine the dimensions of pi. The diameter is the distance between the edges of the circle on a straight line through the center. This distance has dimensions of length, which we can plug into the equation. The circumference is a little trickier in that we're talking about a curved line around the outside of the circle rather than a straight line for our examples so far. But there's nothing about the dimensions of length that suggests it has to be along a straight line. The circumference still has a length along a single dimension, it's just that single dimension is now curved. After doing the algebra, we see that pi is what we call a dimensionless number. The dimensions of the numerator and the denominator cancel out to unity. This canceling of dimensions is a common property of generalized descriptors we use in nature. A lack of dimensions tends to indicate a normalization of variables that allows the resulting ratio to be more transferable or comparable across different applications. We'll see lots of examples of dimensionless ratios as we move on. Now that we know the dimensions of pi, we can get back to our equation for the area of a circle. The numeral 1 as a dimension represents the dimensionless character of pi. The radius is half the diameter, so it also has dimensions of length. Working through the algebra, we have again supported the dimensional consistency of this derivation from geometry and calculus. And again, we would expect that any system of units would work, and that we can choose any units of length for the radius and get the corresponding units squared as the units for the calculated area. Any equation for area derived from geometric theory should result in dimensions of length squared. If not, there is a good chance you have either made a mistake in the algebra for the derivation, or perhaps you are using an empirical equation that is based on an arbitrary mathematical pattern in data rather than independent geometric theory. Your intuition is probably telling you that we are not quite done with space. To uniquely identify a given location in space, we need a third orthogonal dimension. In a Cartesian system, this is often referenced as a z-axis. 3 dimensions allow us to think about another derived spatial construct called a volume. Volumes are particularly important because they are fundamental to the physical definition of matter, where matter cannot be matter unless it occupies a volume in space. Your intuition is probably also telling you that the dimensionality of volume is likely length cubed, and you would be correct. I will leave it to you to work through the geometric definition of the volume of a rectangular prism. You should be able to convince yourself of the dimensional consistency that supports that the dimensions of volume from geometric theory will always be length cubed. You might try the equation for the volume of a sphere to reinforce that idea. Hopefully, this basic description of spatial dimensions starts to demonstrate the power of dimensional analysis. It provides a consistent language for epistemologically mapping the variables we measure for objectivity in science with the property those variables represent in nature. If you Google dimensional analysis, you're likely to get a lot of hits to the unit factor technique for unit conversion. However, dimensional analysis is a much more powerful epistemological tool than unit conversion alone, and deserves much more attention earlier and more often in the training of environmental scientists.